So in the last section, we have discussed already the basic steric inhibition of protonation and steric inhibition of resonance. And as you have discussed, that we're going to learn proton sponge in this class. Okay. So in proton sponge, there are some molecules called proton sponge. Suppose there is a sponge molecule. In sponge, what happens? In normal sponge we use in home, or we use in different electronic ingredients packages. So the sponge has very fine pores, and in that pores, if we dip it into water, a bucket of water, let's say, if we drop it in it, then the water molecules get trapped in these pores. So if we put a small piece of sponge in this bucket, then we will be having that almost every pore of the sponge is connected, is filled by water molecule. That means this sponge has very much affinity to water. Now, our topic of discussion is proton sponge. Proton sponge. That means any type of sponge that has very high affinity to proton, right? Let me write in a proper way. Affinity to proton. And we know affinity of proton. Which type of molecule show affinity to proton? These are basically base. So normal bases show affinity to proton. But these bases are normal base. These bases are proton sponge. That means it is a very, very strong base. That is like sponge that abstracts so many protons. Okay. So that means proton sponge are basically bases where basicity is very high. It is very high. Now, I'm starting the discussion with one observation. Okay. I am writing two molecules. For example, this is one experiment. This is one experimental observation. Okay. This is N-ethyl ethyl. Here is N-ethyl ethyl, and here OMe OMe. This is one molecule. Another molecule is N-ethyl ethyl. So these are two molecules. Experimentally, it was found that the pKa of this molecule is 16.3 and the pKa of this molecule is 5.7. Now, you know, if we want to compare basicity, then a pKa is proportional to basicity and pKa is proportional to 1 by acidity. So, which one is more basic among the two? First one. It is more basic. Why? Not because this is a spider-like structure, but yes, there are different reasons. The reason here is, here the nitrogen have one lone pair. This nitrogen have one lone pair, and there will be too much electronic repulsion. The steric repulsion is already there, but to overcome the steric hindrance, these four ethyl groups will be far apart. This bond can rotate freely, right? So to overcome the steric hindrance, already this 4-methyl group has turned down in such a way that they are far apart. So now the lone pair repulsion become prominent here. When this molecule will undergo protonation, what will happen? Simply, this nitrogen, for example, this nitrogen have abstracted the proton. Ethyl, ethyl. This nitrogen, sorry. Okay. This nitrogen, ethyl, ethyl, and the lone pair. Now this nitrogen is now positively charged. The nitrogen which abstracted proton is now positively charged. Then there will be a certain kind of stabilization with that lone pair of nitrogen and the positive charge of nitrogen. This is like this. If I zoom it, N, ethyl, ethyl, hydrogen, ethyl, ethyl, positively charged. and now this is lone pair. Hydrogen is also delta positive, so it can connect with this way or it can connect with this way. So this kind of stabilization it gets when it undergoes protonation. So when it was deprotonated, it was very much sad. Why? Because it has two very high repulsion. But when it has just protonated, now its sadness is over because no, there is no two lone pair, so repulsion has reduced. But it is very much happy because the lone pair is now stabilizing with these two groups. So it was sad, it is now not just normal, it is very much happy. So that's why this type of molecule has very high tendency of abstracting proton. That's why this type of molecule is called proton sponge. This is not proton sponge. First one, it is proton sponge. Okay. Now, uh, now you are very sure that more the steric hindrance or more the lone pair will be come closer, then the more will be the steric repulsion, and more it will have the tendency of abstracting proton, and it will be a better proton sponge. That means lone pair repulsion, if high, then um, sponge, it will be a better sponge, so basicity will be higher, right? Okay. If the steric hindrance is high, for example, this group is very much bulky. If this group were less bulky, then what would happen? Then this would have less tendency to go beyond this, because it is a system of free rotation. If this is not that much bulky, these groups are not that much bulky, then the group will freely rotate, and the lone pair will not that much come closer. That means this will not generate that much of you know that much of steric hindrance. Okay, so if the group is small, then this group will can rotate freely very well, then the lone pair repulsion will be less. That's why there will be no much tendency to abstract proton like a very high proton sponge. So proton sponge behavior will be less. If steric hindrance is higher, then it will be sponge will be higher, then the basicity will be higher. If steric hindrance is low, then basicity will be low. Very simple. Now I am showing you one example, and you try that what should be the basicity order. Write the question with me and try to solve yourself. N Me2 N Me2, 6-member ring. Okay, biphenyl system. N Me2 N Me2. Third one is, here will be nitrogen in that center. This is not carbon, it's nitrogen. Pyridine type of system. Okay, these are our three molecule, and your task is to predict the basicity. First, second, third. I will be giving you 5 seconds, and till then try yourself. 1, 2, 3, 4, 5. Okay. Now, if these two nitrogen is more closer, then there will be more steric hindrance. So that will be better proton sponge. Now this, which carbon here is more closer? See, here this nitrogen and this nitrogen is 4 carbon distance. Isn't 4 carbon distance? Here also 1, 2, 3, 4 carbon distance. But here you will notice that it is 3 carbon distance. So these are basically closer. No matter how I have drawn, examiner can give you a drawing in any way. Okay. So here just you have to think logically. There are 3 center. So these nitrogen are basically closer. Okay. this lone pair, they're very closer. So 3 will be the strongest base, that means best proton sponge among these three. Now these two. Now it is basically a geometrical phenomenon. If there is a six-member ring and it is basically connected to in a six-member way, and it have to connect in a five-member way, uh, it is the fact that the six member, for formation of a six member, these nitrogens are basically far away. This two group is far away enough. Okay. Sorry. This nitrogen, if it is six member, then this lone pair will be more oriented to a closer geometry. But here, actually, I have drawn like this. But if as it is a five-member ring, you can think of like this. These are two different group. Okay, so these are basically far away, but this is closer. So as this is closer, then it will be better put on a sponge, then two, then one. So this will be our order. For example, similar kind of example, if I write, this is from a research paper, and let me give you that example. For example, in mm, N Me2, N Me2. Second structure is N double bond N Me2, like a guanidine type of system. N Me2. Mm, N Me2. N Me2. It has a name. Just forget. I have forgotten that. The full form I have forgotten. TMGN. This is called TMGN. Maybe tetramethyl guanidine type of proton sponge or something. Okay. Last one is similar kind of structure. N double bond P N Me3 N Me3 N Me3 double bond P N Me3 Me3 Me3. Okay. Now, which one is most bulky? I've told you the most bulkiness. The second point I've written, the more bulky, more will be toward the lone pair will be facing each other and more the repulsion. So 3, if it is 1, if it is 2, if it is 3, then 3 greater than 2 greater than 1. Okay. Okay, so this is the discussion of proton sponge. Okay. Another example, popular example, let me share with you. Okay, it's right here. The question is last question of this discussion. N Me2 N Me2. Second one is obviously N Me2 N Me2 N Me2 and O methyl O methyl. Third one is N Me2 N Me2 in para position O methyl O methyl. One, for example, let us give its name XYZ XYZ. Try yourself. I'm giving you time. 30 seconds. I'm waiting. Try yourself. Here the answer will be Z greater than X greater than Y. Why? Let's see. In Z, what will happen? This OMe will show resonance, and with that resonance, the nitrogen lone pair, the nitrogen center, the negative charge will be there. So lone pair will have more repulsion. Okay, this negative charge, if I write in another way, this OMe will put negative charge over ortho position and para position. With the repulsion of this negative charge, with the repulsion of this negative charge, lone pair will get repelled more. So more repulsion in lone pair will increase the repulsion in this level also in both the side. So overall, due to these two repulsion, uh, the uh, the electronic repulsion of lone pair will be much more higher in case of Z. But you can have another question, because in this segment, here also it will be getting negative charge. Here also negative charge. For this oxygen, here will be negative charge. Here will be negative charge. In this case also, we are getting that the negative charge is there. But what will happen? We know OMe group shows plus R effect and minus I effect. For plus R effect, it is giving negative charge. But as it is far away, with the minus I effect, with the sigma bond, it cannot drag the negative charge to it. But this negative charge will be dragged by this oxygen. Okay, this is one explanation. Another explanation is, with that steric hindrance here in this segment, that a steric hindrance is not present in this. With this steric hindrance, this bond can rotate or this can rotate, and for this, because it will rotate a bit, this oxygen will rotate a bit, and due to this rotation, the oxygen will not able to actually generate much more negative charge in these positions. Okay, this is basically steric inhibition of resonance kind of thing, isn't it? So so for this bond rotation, oxygen will not able to generate the plus R effect. So plus R effect will not be there, but oxygen what will do, even if it is rotated, but sigma bond is still there, so it can perform minus I effect. So from minus I effect, it can drag negative charge from there. So lone pair will be dragged by the OMe. So here lone pair will be dragged by that OMe. So here repulsion will be very, very less. But as there is no electron withdrawing group here that is dragging the electron, so here repulsion will be higher. Here will be repulsion will be very much higher. Here higher. Here repulsion will be lower. That is the simple explanation. So in this last example, you have to consider the electronic effect. Okay, electronic effect with proton sponge. So these are all type of question. These are basically some question asked in some previous in some examinations previous year also. So I have discussed the different type of questions that comes in exam. So these are sufficient, and generally books have not discussed about these things in much details. Okay, that's why I have taken some examples from research paper also. Okay, so this is all about proton sponge. It's a very beautiful sponge that is abstracting proton, and basicity is very, very much higher. So in any basicity comparison, if you find one proton sponge is there, so you have to mark that it's more basic. If another example, if some other structures are not proton sponge, these are very, very much stronger. Okay, so I hope you have understood it. If you want any other topic to be covered, you can tell me. I will try to cover them. Okay, bye.